So the last time I introduced how the Chern-Simons theory is embedded into the string theory, and there's a geometric transition between the two configuration when you take large n in one configuration. And today I would like to see how the partition function look like, and which will lead to non-trivial conjecture of the knot invariance. That's what I would like to talk about. And everything today I'm going to talk about in refined topological string theory. So not the ordinary topological string theory. So the refined means there is a two equivalent parameter. So there is a equivalent action like this way. And yes. So the first I'm going to talk about briefly talk about refined Chern-Simons theory, and the next I'm going to talk about how you compute the topological string partition function in the resolved conical side. First, I'm going to talk about the partition function without M5 branch, this M5 prime branch, which will lead to the refined Gopackman-Baffa branch. And the partition function and with M5 branch will give you some so-called refined Elomov invariance. Both are so-called enumerative invariance of the Calabi-Yau manifold. So therefore, this geometric transition or large n duality provides a relation between knot invariance with enumerative invariance inside a resolved conical. So that's the goal of today's lectures. Okay, so let's briefly talk about the refined Chern-Simons theory. So the one, yeah, refined Chern-Simons theory. Okay. So the refined Chern-Simons theory is, as I mentioned to you, use the configuration, this brane configuration, like here and here. So here you have 3D n equal to 2 theory, and here, so you have refined Chern-Simons theory. The refined Chern-Simons partition function is defined as the index of the 3D refined Chern-Simons. So of the 3 manifold S3. So let's talk about the refined Chern-Simons theory partition function. It's trace of -1 to the f, q to the j1 minus sr, and t sr minus j2. Okay. Where j1 is a Cartan. So j1 is a Cartan. So this is the Cartan, the spin of SO 1, 2. I mean, I'm working on the Euclidean, so SO3. And the J2 is the U1 R symmetry. So I will explain to you more in detail in latest lectures about the 3D n equal 2 theory. The 3D n equal 2 has a U1 R symmetry. And there is another. So this is extra U1 global symmetry. So when you replace S3 as you can replace S3 as a cipher manifold in general, but if the M3 has a following structure, the S1 vibration over Riemann surface, M3 is called cipher manifold. And in particular, S3 is also belong to the class of cipher manifold. And there is the S1 symmetry. There is a U1 SR. Okay. U1 SR symmetry, which acts on the fiber. So therefore, this symmetry can be seen at the 3n equal 2 theory. So the Differential partition function, yes. And also, when you have S inside a knot, you can also have a knot inside a S3, or in general cipher manifold, but you have to preserve this S1 symmetry. Okay. In order to preserve this, the S1 symmetry, so this U1 SR symmetry, so that the knot has to be, so if the M3 is the S3, and then knot is the so-called torus knot. So as I mentioned, explained to you, the torus knot is the so the torus knot is a knot which can be put on the torus. If the knot is torus knot, so you can preserve still this as the U1 symmetry. So therefore, so this defined transform theory can be only applied in the case of torus knot. So you cannot apply you cannot consider refined transform theory in arbitrary knot. Okay. Only for torus knot in S3. This preserve U1 SR symmetry. And let me be brief here a little bit, actually. So the working definition. So this is very, an abstract definition of the refined transformer theory, and the Aganagi Shakirov gives us Shakirov gave a working definition, so that they just give you to compute, as I mentioned to you, to compute not torus not imbalance, you only need a S and T matrix, SL to the matrix. In particular, so the Aganagi Shakirov give the following the working definition of the lambda and mu are the representation. I think last time I used R1 and R2, I think. Let me change the notation. This notation. And the rho is a Weyl vector. And the P lambda X and the QT. I just want suppress Q and T here, actually. It's a Macdonald function. Macdonald functions. S00 is a partition function or refined transformer S3, which I don't think it doesn't play any role, so I'm not going to write it down in the lecture. So in the Q is the delta. Again, it can be the diagonalized, whose eigenvalue is given by Q to the 1/2 lambda square and Q to the 1/2 lambda transposed square and T to the n over 2 lambda T to the 1 over 2n and lambda square, where the lambda is the representation. So therefore, so you can sign define Chern-Simons theory. So the yes. So this is a long. I mean. So the long story. So the index. Okay, how I get this one? I will explain more in detail around here, but the index can be considered as the. So index can take the following form: exponential of the sum of n 1 minus d. How do I get this one? Yeah, I mean, so index has a following form. It's a single partition function QD and TD, and there is a index, and with the some Fravor symmetry S mu of x actually. So S mu of x. So the 3D n equal 2 index can be just count that this is called single letter index. This is the, and this S of mu is associated to the Fravor symmetry. Fravor symmetry means if there is another global symmetry, you have to put the x to the something, x to the Fravor symmetry. Okay. In particular, when you consider the so when you consider the partition function, so when the M3 is just solid torus, this is reduces to when M3 is equal to solid torus S1 cross D2. S1 cross D2, then the partition function of this refined Chern-Simons of S1 cross D2 is given by the exponential of 1 minus t to the n, sum of d, 1 minus t to the d, 1 minus q to the d, and 1 over d, and x d, x d xi minus d xj. Yeah. So that's what you're going to get actually. The xi is the holonomy. So xi, you have to put the boundary condition on the torus, and that is described by holonomy actually xi. Yeah, yes, 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 yes. Um, mhm. What is the map? Oh, good. Yes, that's good question. Um, that's good question. Um, hmm. So what is the um, how can I explain to you? What is um, 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 I mean, it's very hard to explain. Mhm. S3, yes, yes. Yeah, then you just have a growing of the. Yeah, so the what you get is as follows. So the so this is actually equal to the so-called McDonald measure. What was it? So this is actually equal to the McDonald measure. So this is equal to beta minus 1, m equal to 0, and so sorry, I think I should mention that this one includes uh, sum of 1 xi xj n e to the d xi minus d xj xj. Let's miss this one. Where the um, q to the minus over m minus m over 2 xj minus xi over 2 and minus q m over 2 e to the xi minus xj over 2, where the 1 I j n, so this range. And let's go, this is delta q and t and x. Then um, and GS3 is given by this is what analytic structure of state is as follows. So you have the so this M of L. So this is S1 cross D2, and Z S1 cross D2, and e to the minus trace x squared over 2 to epsilon 1, where the epsilon is the q to e to the epsilon is equal to q. So here, you have a one index for S1 cross D2. So S3 is as I mentioned. So S1 cross D2 and S transformation and S1 cross D2. That's a two copy. Sorry, with S transformation, and then you just bring a two copy of index, and this is actually S transformation of the 3D N-2 index. I will explain later. And what you're going to get is the as follows. So this is the sorry, I should mention what is beta. Beta. So I just put a T Q to the beta, where beta is some natural number. So beta is this relation. Yeah. So what's so this guy? Yes, that's the answer in the case of not. Yeah. And this is the S00 actually. This is S00. And I just give you answer. So this is some over some constant, some number constant times beta minus over 2 minus 1 m equal to 0 n minus 1 I runs from 1 q to the minus m over 2 t to the minus I over 2 minus q to the m over 2 t I over 2 n minus I n minus I. Okay. That's what's going to get for S00. In particular, so this delta qt is actually called Macdonald measure. It's called Macdonald measure. I will explain later what the Macdonald measure means. The reason why you get this one. Okay. Is it okay? Is it much better? Okay. Okay. So okay. I think I should explain much more precisely. Okay, so the um, so the this so and I should mention that this will reduce. So when you take an unrefined limit, q equal to t limit, which means the beta is equal to 1, I think. This will drop off, and when you take q equal to t, what you're going to get is the what I have written down before. So what I have written down. So this is the proportional to this is proportional to the sum of the. I have written down like this, right? K over n over 2 to the n minus I is equal to 1, 2 times sine pi j, pi I, k plus n, okay, to the n minus I. Okay. So that's what's going to happen when you take unrefined limit. So this is unrefined limit. Okay. Excuse me. Then, so yeah. So what's going to happen is follows. So the question is how to get this term. This term. This is a single particle index of S3, and so as we recall, so if you recall, so you have a S3, and there's the N M5 branch, and there's a yes. Oh, sorry. Oh yeah. Just a moment. How does it arise? So there are only two bosonic fermionic particle coming from the D2 brane ending on D4 actually. It's hard to explain. There is a solid torus S1 cross, and there is a cotangent bundle. So I'll set up this T star cross S1 cross D2. And the D4 brane wraps on this solid torus. Yeah, that's true. This is very hand-waving argument, which I cannot explain very well. You just get the fermionic bosonic particle coming from the M2 brane attaching on the solid torus, and the single particle index will give. So this will contribute to bosonic particle, which with single particle index 1 over 1 minus q, and the fermionic single particle index, which will give you minus t over 1 minus q. So this denominator, this is index of the bosonic. The single particle index of the fermionic is minus t. So the denominator come from the derivative. So this with respect to this q plane. So derivative come from this q plane, and T coming from charges of the so U1 charge of Q U1 charge coming from here, and so if you sum them up, what you get is this part of index, and everything is actually colored by only single boxes. So therefore, if you substitute single box, what you get is this one. That's what Shakyov mentioned. Then so this is what you're going to get the McDonald measure. And the argument is if you put the some Wilson loop inside the solid torus I colored by lambda and mu, then S lambda mu, then what you're going to get is dnx, and here you have the McDonald measure Q and T square of x, and e to the minus trace of x square over 2 epsilon, and the McDonald function T lambda, and e to the minus x, and p lambda e to the x lambda mu. So that's their argument. Yeah, I don't have a good actual explanation about how you get this single particle index. I mean, the argument is very, hand waving actually. Which one? This one? This one. So when you integrate over this one, what you get, so the over x is, then what you got into get is this one, S00, S00 p lambda t to the rho, and this is the standard McDonald. You can use the technique in McDonald functions. I think you just perform you just residual integral of x, and what you're going to get is this one. I don't have a good explanation about how you get this single particle index, unfortunately. But so index of this solid torus is given by this single particle index times show function, and what you're going to get is McDonald measure. Without this one, without S transformation, this integral will. So without this transformation, what is it called McDonald measure? So this dx to the n delta qt of x, p lambda of x, and the p mu of x. E to the x. E to the x, e to the minus x, is given by delta lambda mu with the some function g lambda qt. That's what's going to happen without this matrix. So that's what you're going to get. So that's why it's called McDonald measures. So delta is called McDonald measure. And so this index appears in the S matrix, and T matrix can be obtained by just finding the matrix which satisfy the ST T cube is equal to S squared and so on. So the standard SA to D transformation. Sorry, I don't have a good explanation about this part actually. Okay, let me move on. So I only find the S matrix is given by shear function Q to the rho. So when you take Q equal to T limit, so this reduces to the ordinary undefined S matrix. Rho plus lambda. Okay. So McDonald function reduces to the shear function. This is McDonald and shear function. So therefore, then one can compute the Wilson-Lewis expectation value of the defined Chern-Simons of the torus knot, which depend on Q and T, by again they just take the matrix modification. So especially T the lambda is a color, is the 0 S and a bunch of matrix. That's what I already explained to you. So here I just write down the SA to Z matrix. Which is written by the multiplication by S and T matrix. Then furthermore, when you take Lagrange limit, so when you take Lagrange limit, so you can take some A is equal to T to the N. So this is Lagrange limit. Of refined Chern-Simons theory. Invariance, such that when you take Q is equal to T limit, the unrefined limits give you hopefully PT polynomial. Is that okay? Okay. Okay, hold it pretty button. And then, so the deform, I call deform conical side is I call the index so index of the, so this deform conical side trace of minus at f. So this one, q to the j1 minus sr, t to the sr minus j2, and some flavor fugacity, f. And this is again, so I can write down. So in the case of the torus knot, so this is in the case of torus knot. Sorry, torus knot. Then this will give, can be written in terms of mu 1 over d t d over 2 minus t minus d over 2 q d minus 2. I mean, I just changed the notation. I think I should use the same notation. Sum of index of h mu torus knot and n q and t d and d and s mu xd. So this is the standard form of index. And so from here, so one can just expand the form, refine Chern-Simons, lambda t n n qt and p lambda x q and t. So lambda is a partition function. This is very similar to what Rastelli, Wenbin-Yang, and Razaman has done. So once you have the precise exponent, one can expand some symmetric function, and this is the expansion. And g lambda q, as I mentioned to you, g lambda qt is a Macdonald measure. They just Macdonald measure, which is the d to the nx p lambda of x and e to the x and a p lambda e to the minus x. So this part gives rise to this part actually, and this part, single particle index, gives rise to the Chern-Simons index. Shear function gives rise to this is the Macdonald function. So therefore, so this partition function is a generating function. So it can be considered a generating function. Function of the R Chern-Simons. Yes. Yes, yes. So the undefined limit, when you take, undefined limit, this becomes Jones polynomial lambda k q and the show function of x, lambda, lambda. This is the, when you take q is equal to t limit. Yeah. But this part, actually, I can explain because this is in my paper. So I already, let me erase this first. So when you write and then 5 and upon S3, this is cotangent bundle S3, and there is a Konoma bundle. This is NK. The BPS particle always come from the M2 brane attached between the Lagrangian submanifold. So there is a M2 brane attached between 2 and 5 and M5 and M5 prime, and it turns out that so it gives you this M2 branes gives rise to the M2 branes gives rise to the n equal to 2 chiral superfield phi, which is transformed by fundamental in SUN and anti-fundamental in SUN. Another representation is n bar, and there are 2 chirals, n equal to 2 chiral superfield 2. And if you compute the single letter partition function, so what you get as follows. So this is 1 minus t half 1 minus q, and here you get the t1 half minus just t. Okay. So what you get is single. This contributes to single letter partition function to this one and this one. If you sum them up, what you get is this one. This part. Okay, so therefore, so this is the generative partition function deformed on F4 side. And let me explain to you about how you compute. I just want to make a comment about this one. Sorry. So this large and limited refined transformer invariance up to change a variable this is coincide with this constant with the super polynomial. Super polynomial I explained yesterday. The super polynomial is the Poincare polynomial half triple graded homology. Okay. So now let's move on to resolve conical side too. So the resolve conical side. I would say topological partition. So the topological partition, refined topological partition function. Partition function. Without M5 prime brands. So the CL stands for closed. CS stands for closed. So as I mentioned to you, the free energy of the refined topological partition function can be obtained, in principle, obtained by evaluating by string perturbation theory by using to the force f of g a Karamah superfield WAB and WAB and G, and where WAB is a graviphoton field, and 1/2 TAB plus RAB CD theta A theta B. No, sorry. As first theta CD. Theta. Okay. And so on. Maybe minus sign. And so on. And where TAB takes the following form: epsilon 1 minus epsilon 1 and epsilon 2 minus epsilon 2. So that's is the omega background. Okay. But what Gopakuma mentioned as follows: Gopakuma Buffer proposed, instead of using a string perturbation theory, one can sum up FCL can be computed by summing up BPS states. In M theory. Okay. So to sum up BPS states, so this will I will use a SUSY version of the Schwinger computation. Schwinger computation. So if you use a string perturbation theory, one has to evaluate this FG for each genus, whereas the Gopakuma buffer mentioned that one can do the whole thing, but if you uplift the M theory, that's what I'm going to explain. So, as I mentioned to you, so if you look at if you do the some Calabi-Yau 3/4. Now X can be any Calabi-Yau 3/4. So now X can be any Calabi-Yau 3/4. And then once you compactify on a Calabi-Yau theory on a Calabi-Yau 3/4, what you get is the 5D gauge theory. This is 5D gauge theory. The whole system only preserves the 4 supercharges, but so it it breaks half supersymmetry because of the omega background. So therefore, so let's consider the following 5D perspective. This SUSY algebra in 5D. In 5D, with let's consider 8 supercharges. Then Q alpha I cross Q alpha dot I, which preserve is transformed by SU2 left cross SU2 right cross R charge, SU2 R charge. 5D or 4D or 4D. Depends on how you. If you compactify on S1, you get a 4D thing. And the SU2 left and SU2 right is the little group. The Lorentz symmetry 4D. And the SU2 right is the R symmetry of the 8 supercharges. So therefore, I is the index. So this is capital I, and alpha dot. That's the notation. And the supersymmetric algebra is as follows: Q alpha I, Q beta J, delta alpha beta, epsilon ij, H plus Q alpha dot I, Q beta dot J, and epsilon alpha dot beta dot epsilon ij, H minus C, and Q alpha I, Q beta dot J is equal to minus I gamma mu alpha beta dot P mu and epsilon ij. So this theta is the central charge. Central charge of the 5D gate series, 5D or 4D, yeah, 5D. And necklace are defined the BPS states which counts at the index. Necklace are defined index. Define the following the partition function in 5D point of view. It's very similar to the QL 2JL QR 2J R minus SR to the e to the minus beta H, where the QL, so QL is QT half, and the QR is Q over T and half. Okay? And JL is the spin of the generator of the spin SU2L, and JR is a generator of SU2R, small r, and the SR is the generator of the R symmetry. Okay. Yes, question? So without omega background, then so if you start the M3 or type, if you compact from S1 type 2A, so you have total system 32 supercharges. But if you put on the Calabi-Yau 3/4, it breaks it breaks the 1/4 quarter. So therefore, it produces 8 supercharges. Okay, and as I explained to you, the BPS states that contribute to the index is only the only left-handed BPS MOSFET. So the 0, 0, 1 half plus 1 half 0, 0. So this is n times JL, JR, and SR. Okay. So this is called only left-handed short multiplet. Short multiplet contributes. Yes. Okay. Yes, the private index. So the index partition function of this 5D, S1 cross R4. Yeah. That's the negative partition function. So the index counts the number of the BPS states, which is annihilated by these supercharges. Oh, so that's, for instance, let's do the following counting. Let's see. So for instance, the right-handed MOSFET is the 0, 0, 1 half, the 0, 1 half, and 0. Okay. 1 half. So this is right hand. Okay. Then this contributes to the here, but oh my goodness, yeah. So this part contributes QR plus QR inverse. This MOSFET contributes Q, whereas here you have a Fermi number -1. So it's only have a spin 1 half in this Lorentz indices. So this is, sorry, I should mention JL, JR, and SR. The same, JL, JR, and SR. Okay. So therefore, if you count JR plus inverse, because of the here, you just substitute here. 1 half and a -1 half here. And what you get is 0. Okay. So therefore, F is the 2 times JL plus JR, small r. Okay? So therefore, right-handed multiplet does not contribute, even though you multiply. So the right-handed short multiplet is this one, JL, JR, and SR. Okay? And the long multiplet is this times this one. So therefore, since this is 0, so long multiplet does not contribute. So therefore, only this left-handed short multiplet only contributes. So therefore, yeah. So the supercharge annihilated by this one, annihilated by this one, this part, the right-handed supercharge will contribute to the index. So therefore, only if you turn on this omega background Q and T, so omega background breaks the half the symmetry, omega background. Okay. And here, so you can always multiply. the finite dimensional representation. This is the finite dimension. Finite dimensional rep of SU2 left cross SU2 right cross SU2 R symmetry. Okay. And if you substitute, if you define I just want to consider the higher dimensional representation of the Lorentz and R symmetry. That is also annihilated by these superjudges. The states is there are infinite many states. Okay, infinite many states. So you have only, if you consider this one, this is only this part is called half hyper MOSFET. And there's the infinite many states, and which are labeled by these representations. Infinite many BPS states that contributes to the index that is labeled by these finite dimensional representations. Then, if you consider only this space, only you have a 4 states, but there are infinite many states, and they are labeled by these finite dimensional.
Why are they invalid QR protocols?
Why they contributes to the if you tensor with hypermultiplet, that is the, let's see, that is the states annihilated by these supercharges. How can I explain it? Why do I tensor? And how does it there? How can I I mean, Okay, okay, thanks. Um, so therefore, okay, sorry. I mean, all the states label added by this right supercharges takes the following spin content, and right-handed short multiple do not contribute. Multiple do not contribute to the index because of this one. And even if you tensor this one, you just multiply some number by 0 times 0. Some number times 0 is always 0. So this number comes from this spin content, JL, JR, and SR. Whereas here it contributes to the index. How they contribute? This part contributes to the as you can easily see. So this hypermultiplet will contribute to the index. This is good exercise. And then this is so the JL contributes to the QL. Okay. So therefore QL plus QL inverse. And you have to multiply -1 actually. -1 and a plus, and this part contributes to here. So therefore QR plus QR inverse. Okay, hypermultiplet. Can you see that? So this part contributes to here. Okay, so the 1/2, you substitute 1/2, you get the QR inverse, and if you substitute -1/2, you get the QR, and from here, so it contributes. It's a ferromagnetic field, so you have to have a negative sign here, and if you substitute 1/2 here, you get the QL, and if you substitute -1/2, you get the -QL, and this is equal to Q1/2 minus Q -1/2, and T -1/2, and T 1/2. Okay. Just plug into this one here. Okay. And so if you define the following content, so if you define the SU2L cross SU2 right, and if you take the diagonal subgroup, SU2 diagonal, and you can take the SU2 left cross SU2 right, and the SU2 anti-diagonal. And so I just call J1, which is the JL minus plus JR. The generator of this SU2 is JL minus JR. Okay. Then if you use this expansion, this is the same as trace of -1 to the F, Q to the J1 minus SR, T to the J2 minus SR, and E to the minus LH. You just plug into here and use this relation. What you get is this one. So therefore, this is what we saw in the refined Chern-Simons invariance, whereas refined Chern-Simons invariance is defined by index, and which takes the following form. Whereas in this case, J2 is this anti-diagonal part, and SR is the SU2R symmetry. Okay? So therefore, the refined Chern-Simons index is actually motivated by Nicholson index, and as we will see later, so if you put the M5 prime branes, so this SU2 diagonal becomes SO3 Lorentz, and if you put M5 prime branes, and the U1R symmetry is this SU2 diagonal, SU2 anti-diagonal, U1 part is give you the R symmetry of the 3D angle 2. Okay. And the extra SU U1 SR symmetry is also the U1 part of SU to R, which is here. That's what's going to happen once you put the M5 prime branch. Okay. Then how we compute this index? Okay. um, and this free energy can be obtained by the supersymmetric analog of the Schwinger computation. Trace of -1 to the f, q to the s j1 minus sr, and t to the s sr minus j2, e to the minus n over q s over 2 minus q to the minus s over 2, t to the minus s over 2 minus t to the s over 2. This is the Suzy of the Schwinger computation. So the original Schwinger computation is to compute one loop determinant of the charged particle in the presence of magnetic field. In this case, if you look at the S1 cross R4 QT and the Calabi-Yau 3, the BPS states always come from M2 brane wraps on 2 cycle. The BPS states come from M2 brane wraps on S1 cross some cycle, holomorphic cycle sigma. And therefore, it runs this M0 cycle direction in the presence of omega background, which is a graviphoton field. Therefore, one can apply to the similar Schwinger computation. It takes the following form, and the denominator comes from as follows. So this so we have the TAB takes the following form: epsilon 1 minus epsilon 2. Epsilon 1 and epsilon 2 minus epsilon 2. And this is the Q plane. And from Q plane, so this part is a Schwinger computation. So you just sum up the lambda level of the lambda level charged particle in the presence of magnetic field, which is Q1/2 minus Q to the minus 1/2. Okay. This part comes from this contribute, this plane. Okay. This plane. And the other plane, so this part is coming from this plane, if you do the same computation. And the denominator coming from other, so the massive BPS particle. And if you use the Poisson summation, one can write D is equal to 0 sum of beta H2 xc such that 1 over D trace of minus 1 to the f q to the d j1 minus sr t d sr minus j2 e to the minus d beta tau qd over 2 q minus d over 2 t minus d over 2 minus t d over 2. Okay. So the beta is a 2 cycle of the Calabi-Yau, which this homomorphic cycle on the M2 brane wraps. And tau is a Kähler parameter. This is a Kähler parameter. And from here to here, you just do the Poisson resummation. Which is the, you just on a form 2 pi I and S, n is equal to sum of d delta and S minus d. Okay. And so the rest of the task is to evaluate the numerator. What? Okay. So the numerator is okay. So let me give 5 minutes is fine. 5 minutes. It's
very close.
okay.
Can do that later.
Okay. The then so I just want to mention how you evaluate numerator. So the numerator is obtained by the zero mode, Fermi-Eck zero mode on the M2 brane. And this Fermi-Eck zero mode is actually a cohomology group of the modular space of. So this is modular space of the holomorphic deformation. Okay, in the Riemann surface. This is M2 brane wraps on sigma G. And takes the following form. So the modular space is, I call it the M closed, and the M holomorphic deformation. Okay. And if you evaluate the cohomology of this one, the F just closed is given by maybe D 0 D charges. 1 over D minus 1 to the F n hat G beta JR Q D over 2 minus Q minus D over 2 and T D over 2 minus T D over 2 G and sum over J R so this is sorry, minus 1. Sorry, minus 1. Minus 1. So I just want to mention, yeah. And this is called refined Goldbach-Markov buffer imbalance. This is called refined Goldbach-Markov buffer imbalance. Okay. So yeah, anyway, I have to stop here. Unfortunately, I don't have time to talk about alarm imbalance. Maybe some other time.